All right, so we can now move on to section 2.2, which introduces the limit of a function. This is our first major calculus concept, so I am excited for us to get started with this. Okay, so before we talk about what this is, I want to talk a little bit about why we need it, okay? So let's think about the functions. Let's let f of x be equal to x squared minus 4 over x minus 2. Let's let g of x be equal to the absolute value of x minus 2 over x minus 2. And then let's let h of x be equal to 1 over the quantity x minus 2 squared. Okay, so let's think about what all of these three have in common, okay? What's the same about all of these? Well, if I look at all of them, in the denominator, I have x minus 2, right? So what this means is that for all three of these, the function, so I'll just write it as all of these functions are undefined at x equals 2. And I know that because if I were to plug in a 2, it wouldn't work out, right? And so what I know is that on all of these, I cannot plug in a 2 for x. But based on the knowledge we have so far, that's really all I can tell you about all of these three, okay? That's all I can say. And so your initial thought would be, okay, well, since they are all undefined at the same point, that means all of these do pretty much the same thing. But that isn't true at all. In fact, if we graphed these, we could see all of these do something completely different at x equals 2. Okay, let's actually look at that. Let's graph these. So the first function was f of x. F of x equals, we're going to make a fraction, x squared minus 4 over x minus 2. Let's see what that function looks like. I'm zoomed way in for some reason. There we go. Okay, that function looks like that, but I can see if I tried to look at x equals 2, x equals 2 is right there. It is undefined there. Again, because I can't plug in a 2, right? Well, let's look at the function g of x equals, again, we're going to do a fraction, absolute value of x minus 2 over x minus 2. That function looks like this. It's the green line. The green line over here. Way different, right? Not the same at all. But if I look right there, it is undefined there. And at 2 down here, it is undefined there too. Let me get to 2. There it is. So even though they are undefined at the same point, the functions are not the same at all, right? I can clearly tell that. Let's look at this other function and see what happens there. Let's do 1 over x minus 2 squared. That function looks like this, which is way different. So my point here is that just because we know they are each undefined at x equals 2, they do something completely different each time, right? So like right here, it looks like there's a point on the blue line, but there's just not one there, right? The purple line, it just increasingly goes up to infinity as I go. It's just going to keep going, keep going, keep going, keep going. The green line is split into 2, right? So my point is just knowing that that is undefined at 2 doesn't actually tell me a whole lot. So what I really want to know is what happens as x gets really close to 2, right? I want to know what happens as x gets really close to 2. That's going to tell me more than just that I can't do 2, right? It's going to help me to know what happens as my graph gets really close to 2. So like right here, the blue line, I can see that it's getting really close to a certain point. The green line, I can see two things will happen right here, right? One happens on the bottom half, one happens right here. The purple line, I can see it's just going to grow and grow and grow. So that's what I want to know. I want to know what happens as x gets really close to 2 there, right? That is what we call a limit. Okay, so definition. If a function f of x gets close to a number, we'll just call it L, as x gets close to a number, I'll just call it C, then we say the limit as x approaches C of f of x is equal to L. Again, what this means is as x gets really close to C, the y gets really close to L. Okay? As x gets really close to C, y gets close to L. So looking at those graphs we just graphed over here, I can see the blue line, as x gets really close to 2, I can see y gets really close to 4, right? Because if you look at this point right here, even though there's not a point there, as x gets closer to 2, so like let's drag this along here. I can see as my x is getting closer to 2, my y is getting really close to 4. So I would say that for that one, so for that one right here, using this f, I'll draw a little line, using this f, the limit as x approaches 2 is equal to 4. Oh, that's not a 4, that's an L. I saw this, and so I just put L. Is equal to 4. Again, because if I look at the graph, as x gets really close to 2, my y gets really close to 4. From this side too. As it gets closer and closer to 2, my y gets closer to 4. Alright. So, what I want to practice now is practice finding what the limit is using a table. Okay, so using a table of values. So let's look at an example of doing that. Example. Let's find the limit as x approaches 0 of sine of x divided by x using a table. So I want to know what happens as x gets really close to 0. So how I'm going to do that is I am going to plug in values for x that are really close to that. So I need to do that on the left side, and I need to do that on the right side. So on the left side, I can use like negative 0.1, and then I can use like negative 0.01, and then negative 0.001, and just keep using that. On and on, and I'm going to see what the value is of y for each of those. On the right side, I can do the same thing, but I can use 0.1, 0.01, 0.001, 0.0001. All of those are really close to 0. So I'm going to use those. So let's first plug in negative 0.1 into this guy. So, using my calculator here, we're doing, let me make sure I'm in radians, because that's what we always use in calculus. So radians, we're good there. So I'm doing sine of negative 0.1 divided by negative 0.1. And I get like, I don't know if y'all can see that very well, but it's 0.998, that's enough. I'll just put 0.998, sorry, I'll do one more there. Let's plug in our next point. Sine of negative 0.01 divided by negative 0.01 gives you, that's 0.9, I went 4 spots right here, so I'll do 4 here too, 9999. And then if I plugged in negative 0.001, just keep going, get the same thing, just a bunch of 9s. And then I'm going to get the same thing if I plug in that as well. Let's see what happens on the right side. So let's plug in 0.1. So sine of 0.1 divided by 0.1. Same thing, 0.9983. Plug in 0.01. Same thing as what I got on the left side. And that's actually going to happen for all of these. If you plug them in, you see I'm getting 0.99999, a bunch of nines. Okay. So now what I can see on both of these is as x is getting really close to 0, I'm going to look at the value of y, and I see it's getting increasingly closer to 1, right? This is getting really close to 1, so is this getting really close to 1, so the limit is equal to 1. Because I can see as x gets close to 0, y gets close to 1. I can see that from the graph, too. If I graph the graph, let's get rid of all these. So the function sine of x divided by x. It looks like everything is good, but I see as x gets increasingly closer to 0, y is getting really close to 1. And when I get there, the function is undefined. If I ever can get there. There it is. There we go. But I can see by dragging it that as x gets really close to 0, y gets close to 1. Same thing over here. If I drag it and get really close to 0, y gets closer to 1. So that's why it's equal to 1. Let's look at another example. Oh, and I want to make it clear too. This is actually a fact we are going to use throughout this whole class. So just keep that in mind. We'll talk a little bit more about why we get this whenever we do. I think it's in chapter 4. We are going to talk a little bit more about why this is so cool. But anyway, that's just a fact we are going to use. That's why I wanted to do that with you right here. All right, let's look at another example. Let's find the limit as x approaches 4 of the square root of x minus 2 over x minus 4 using a table. So again, what this means is I want to plug in stuff that gets really close to 4. Okay. So I need to do that on the left side. On the left side, getting really close to 4, that's like 3.9, and then 3.99, 3.999. I'm just getting as close to 4 as I can. 4 should be enough. And then on the right side, do the same thing. I need values really close to 4. So like 4.1, 4.01, 4.001, 4.0001. That should be enough there. And let's plug them in and see what I get. Okay. So, square root of 3.9 minus 2 divided by 3.99 minus 4. That gives you let's write that as 2.5158. Let's plug in 3.99. So that's going to be square root of 3.99 minus 2 over 3.99 minus 4. Did I really get 2.5 there? I feel like that wasn't right. That's really big. I think it should have been 0.25. I think I wrote it down wrong. 0.25158. That's way better. All right, for this one we got 0.2501. That would round up to 6. Plug in 3.999. Square root of 3.999 minus 2 divided by 3.999 minus 4. That would be 0.2500. That would round up to 2. Now let's do 3.9999. Again, we're just plugging in values really close to 4. That would be 0.25000. There's more stuff there, but pretty much that. All right, let's do it on the right side too. Oh, I think I clicked the button I didn't mean to. Square root of 4.1 minus 2 divided by 4.1 minus 4. That gives you 0.2484. That rounds up to 6. Plug in 4.01. Square root of 4.01 minus 2 divided by 4.01 minus 4. That's 0.24984. Plug in 4.001. 0.24998, and then also 4.0001. Put 2 points, going way too fast. 1 minus 4. Let's see, I messed up again. Let's try it again, going too fast. 0001 minus 2 divided by 4.0001 minus 4 equals. There we go. 0.24999, something like that. Basically, as I can see right here, as I get really close to the number 4, I can examine that the limit as x approaches 4, square root of x minus 2 over x minus 4, is getting really close to 0.25. Or if you would rather write it as 1/4, that works too. It's getting really close to 0.25. Let's do another example of doing that. Let me find it in my notes. So sorry, I think my notes got out of order somehow. Let's find the limit as x approaches 0 of sine of 1 over x using a table. So again, we're going to go from the left and from the right. So from the left, I need really close to 0, so I can do like negative 0.1, negative 0.01, 0.001, 0.001. From the right, do the same thing. 0.1, 0.01, 0.001, 0.0001. And let's see what I get when I plug those in. Oop. All right. So that's sine of 1 over negative 0.1 gives you 0.54402. Let's plug in negative 0.01. That would be 0. Trying to write without right there is hard. 0.50637. Next one, sine of 1 over negative 0.001. That gives you negative 0.82688. Let's try the next one, sine of 1 over negative 0.0001. It gives you positive 0.30561. Let's go over to the right side now and do those. Sine of 1 over 0.1, negative 0.54402. Sine of 1 over 0.01, negative 0.50637. Sine of 1 over 0.001, 0.82688. One more. Negative 0.30561. All right, so looking at this one, I can look at it and see this is kind of going crazy, right? This is positive, positive, negative, positive. Same thing over here. The signs are switching. I'm not approaching a single value, right? I'm not getting closer to one y here. They are just going like some are high, some are low, and that kind of thing. So since I'm not approaching a single number, what I say is the limit as x approaches 0, a sine of 1 over x, I say that does not exist. Because there's not a number I'm getting closer to. Okay? Let's take a look at the graph of that and see why that might make sense. So this function is f of x equals sine of 1 over x. I put x over x, I'm going to put 1 over x, like that. Look at this. That is crazy, right? As my x is getting closer to 0, my graph is going crazy, right? I'm trying to zoom in as far as I can. You can see it's going up and down, up and down, up and down, up and down. And it does that the whole time. I can zoom in really close, and it's just craziness. It's going up and down, up and down, up and down. So as x approaches 0, I'm not approaching a single value of the y, right? Because it's going up and down, up and down, up and down, up and down. I'm not getting close to one point. And so that's why that makes sense here. Because I do not approach one single point. All right, the next thing I want to do is I want to practice doing this using the graph, okay? I want to show you a graph, and we're going to find them that way. I'm actually going to use the book. I printed out a few pages of the book to do this with. So that's what this is from. Let's look at this graph right here. This is saying I want you to find the limit as x approaches negative 1. Okay. So what I'm going to do is I'm going to look at my graph, and I'm going to say, okay, as x approaches the negative 1, which is right there, I can see my graph is approaching this point. So as x approaches negative 1 of g of x, I'm looking at it, and my y is getting really close to this point. Now, a point I want to make here. Notice this point is not a defined point, right? The defined point is right here. So some people may think, okay, since my point is right here, it must be equal to, what y is that? 1, 2, 3, 4. So people are going to say it must be equal to 4 because that's where my point is. But be careful there. What I'm wanting to know is what happens as x gets close to that, right? As x gets really close to the negative 1, it's getting closer to this point. So I'm looking at this point. The y value there is 1, 2, 3. So the limit is equal to 3. Again, because I want to know what happens as x gets close to that point, right? So it's getting closer to this point. So it's equal to 3. On that same note, I can look at this example, also pulled from the book. Bam. This one's asking for the limit as x approaches 2 of h of x. So I'm going to look at 2 is right there, so I want to know what's happening as x gets really close to 2. And I see it's getting really close to that point right there. The y there is equal to negative 1, so the answer is negative 1. Even though there's no point there, that's what happens as x gets close to 2. And so that's what I want. All right, so now that we know the basics of finding what a limit is, I want to take this one step further. Okay, so let's zoom back out. Let me fly in another whiteboard. Now I want to talk to you guys about something a little bit more specific, and that is one-sided limits. So we have actually already done these, we just haven't called them that yet, okay? So notice on the table ones we did, I had to go from the left side and from the right side, right? So that's basically what these are, I'm only going to look at just the left side or just the right side, okay? So if you see this, the limit as x approaches a number with a minus sign. If you see this, that means all I want is the left-sided limit. So this means as x gets really close to c from the left. Okay, so I'm only looking at what happens from the left. So this means on the table, I would only do this left part right here. Okay. If you see the limit as x approaches c with a plus sign, that's the right side. So this means as x approaches c from the right. So in this case, I would only look at what's happening on the right side. Okay, so I'd only do this part. So let's do some examples of that. I think I'm going to need more space, so I'm just going to go ahead and get a new board so I don't have to switch out stuff. Example. Let's let f of x be equal to the function. It's going to be x plus 1 if x is less than 2. And it's going to be x squared minus 4 if x is greater than or equal to. So which one of these I'm going to do depends on where x is. Okay. There's two parts. The first thing I want to do is to evaluate the limit as x approaches 2 from the left. From the left side. So I'm only going to look at the left side of this, okay? Because I'm saying approaching 2 from the left side. So the values of x I can use that are to the left are like 1.9, 1.99, 1.999, 1.9999, 4 should be enough. And I'm going to plug those in based on what I have. So since this is coming from the left-hand side, I know I want to use when x is less than 2 because it's on the left side of 2, right? So it's everything smaller than 2. So I'm going to use x plus 1. So I can do that in my head. 1.9 plus 1 would be 2.9. 1.99 plus 1 would be 2.99. 1.999 plus 1 would be 2.999. Same thing here, you get 2.9999. So what I can see is as x is getting really close to 2, my y is getting really close to, I can see that would be 3. So the limit as x approaches 2 from the left is 3. Because as I get really close to 2 from the left-hand side, I'm getting really close to 3. For part B, I'm going to say evaluate the limit as x approaches 2 from the right. So now I'm going to do it from the right-hand side. So I need things really close to 2 on the right side. So that would be like 2.1, 2.01, 2.001, and 2.0001. Now, this is from the right side, and so since it's from the right side, I'm going to use the bottom one. So plug those in. This one I will need a calculator for. So 2.1 squared minus 4 gives you 0.41. 2.01 squared minus 4, it's really close to 0.0401. 2.001 squared minus 4, 0.004001. That's cool how that happens. I didn't even plan that, but that's cool. It's the same thing, just 0401. That's pretty neat. Anyway, sorry. Had to have a little nerd moment there. 2.0001 squared minus 4. 0.00040001. All right, so let's see what's happening there. As my x is getting really close to 2, I can see that my y is getting really small. So the limit as x approaches 2 from the right is going to be equal to 0, because that's what I'm getting really close to. Again, the minus sign just means I'm going from the left side. The plus sign means I'm going from the right side. All right, so you may ask now, why on earth would I want to do this? Why would I want to know what's happening on the left and what's happening on the right side? Okay, here is why. Here is the reason why. So I'm just going to call this like fact. The limit as x approaches c is equal to L if and only if the limit as x approaches c from the left is the same as the limit as x approaches c from the right, and those both have to be L. Okay, so what this means is in order for it to be equal to L, the limits on both the left and the right side have to be the same thing. Okay? Let's think about why. So let's look at this function we just did right over here. So what we found over here was that on the left side, it gets really close to 3, and on the right side, it gets really close to 0, right? Well, since the two sides don't go to the same point, there's not a singular point my graph gets close to, right? Because it goes to 2 points, right? On the left side, it goes to this point. On the right side, it goes to that point. So because they are not the same, what I would say for this case, I don't have as much room as I thought I would. I'll just write it right here. The limit as x approaches 2 does not exist because there is not a singular point I'm getting closer to. There's 2 points. So that doesn't work. Okay? So that's just, I wanted to just make this big point right here. This is a big deal. The limits on each side have to be the same. Okay? Have to be the same. All right. Let's look at some more examples and talk about what's happening with the limits and such. I'm going to do it with an example. Let's find the limit as x approaches 0 from the left of 1 over x. The limit as x approaches 0 from the left of 1 over x. Okay. So I'm looking at the left-hand side, so I'm going to use points from the left. So I'm getting close to 0, so negative 0.1, negative 0.01, negative 0.001, negative 0.0001. Right, because it's asking for the left. So let's see what's happening there. So it's 1 over x. So 1 over negative 0.1 is negative 10. Easy. 1 over negative 0.01 is negative 100. So negative 100. 1 over, you can probably guess what this one is, negative 0.001 is negative 1,000. And then 1 over negative 0.0001, again, you can probably guess that's going to be negative 10,000. So let's think about what this means, okay? Not only am I not approaching a single value here, right? If you look, these are getting increasingly smaller, right? Negative 10, negative 100, on and on and on. This is getting smaller and smaller and smaller and smaller. If I'm looking at it on like a graph, that just means I'm getting like way further down, right? Because the negative 10 is like, we'll say like right here, negative 100 would be further down. Negative 1,000 would be way down here. Negative 10,000 would be way down here, right? So it's getting really small, really low. So what this means is the limit as x approaches 0 from the left of 1 over x is equal to negative infinity, because it's getting increasingly smaller. Okay, it's getting really small. If I did 0.00001, that would be negative 100 to 1,000, right? I lost count. 100,000. So then it would be really small. So it would just keep getting smaller and smaller as I go. Another example I want to do, let's do it from the right-hand side. From the right-hand side. So then points I could, again, there would be like 0.1, 0.01, 0.001, 0.0001. See what happens when I play in those. Excuse me. 1 divided by 0.1 is 10. 1 divided by 0.01 is 100. 1 divided by 0.001, you can guess, is 1,000. 1 divided by 0.0001 is 10,000. So again, just like what it meant over here, this is just going to grow and grow and grow and grow and grow. And so we would say the limit as x approaches 0 from the right of 1 over x is infinity, because it's just going to grow and grow and grow. So let's think about what I can say about the limit as x approaches 0. Well, I can see from the left it's going increasingly down. On the right it's going increasingly up. So we could say the limit does not exist. And the reason is because it is not the same on the left and the right. So it does not exist. All right. I have one more example that I want to show you guys. This one's also from the book. Sorry, I'm getting everything straightened out. Right here. Since part A is not on this page, we'll just go ahead and skip to part B here. Part B first asks for the limit as x approaches -2 from the left. -2 from the left-hand side. So I'm going to look on the left-hand side of the graph. So the -2 is right here. So I'm going from the left towards -2, and I can see my y is getting closer to this point. The y there is 3. So the limit as x approaches -2 from the left is equal to 3, because it's getting increasingly closer to 3 from the left side. Only looking at the left side right here. Now we can do the right side. Limit as x approaches 2 from the right side of f of x. So that means I'm coming from the right-hand side down to -2. I can see I'm getting really close to this point, which is also y equals 3. So since they are the same, I can say that the limit as x approaches -2 is equal to 3. Again, because they are the same thing, so it's going to 3 from the left and the right side. Let's do the same thing for 1. Okay, same thing for the 1 right here. The limit as x approaches 1 from the left-hand side. So I can see 1 is right here. So my graph from the left side is going closer to this point right there. That's x equals 1, right? So on the left side, I'm getting closer to this point, which is y equals 6. On the left side, I'm approaching it right here. But from the right side, limit as x approaches 1 from the right, again, 1 is right here. From the right-hand side, it's right here getting really close to 1. So my y on this point is 3. So from the left side, I'm getting close to 6. From the right side, I'm getting close to 3. So that means the limit as x approaches 1 does not exist, because they're not the same. And so there's no 1 point I get close to. Now it asks for 3, the limit as x approaches 3 from the left. So 3 is right here. As x gets really close to 3 from the left-hand side, it's just going to keep going down and down and down forever and ever and ever and never stop. So that means negative infinity. And then the limit as x approaches 3 from the right side, I'm right here getting closer to 3. Again, it's just going to keep going down and down and down and down and down. So that's also going to be negative infinity, which means the limit as x approaches 3, since they are the same, it would just be negative infinity. Sorry, this was part B, this is part C, this is part D. I just found room wherever I could make it fit. I'm realizing now I did skip a part. F of negative 2. So I'm going to look and see what the y value is at x is equal to negative 2. Negative 2 is right here. The graph looks like it's right there, but there's not actually a point there, right? So that is undefined because there's no point there. For part C, it asks for f of 1. So I'm going to go to x equals 1 and see where the point is. I see my point is right there. So that's equal to 6. And then it also asks for f of 3. 3 is right here. There's no graph at that point. So that is also undefined. Alrighty guys, so that is the basic stuff you are going to need for section 2.2. In section 2.3, we are going to go a little bit more in depth with all of this stuff. Okay, so I will see y'all then.